Okay, we've seen the basic inverse trig graphs and how to draw those. What about some variations, something like this, 5 inverse sine x on 3. If I want to work out the domain, I know the basic inverse sine graph goes in between -1 and 1. But the ratio here is x on 3 rather than just x. So I say, well, x on 3 must go in between -1 and 1. Multiply by 3, I get my domain. Now with the range, I need to group this coefficient with the y. So I do a similar thing, but instead of y being in between minus pi on 2 and pi on 2, it'll be y on 5 is in between. And so then we get our range, minus 5 pi on 2 to 5 pi on 2. Now we can draw our inverse sine graph. Basically, I can draw exactly the same graph as I drew before, just change the numbers on the axes. Whoop, there it is. Y equals 5 times the inverse sine of x on 3. Inverse tan of root 3 minus x squared. Now, the domain for inverse tan was all real x. But when we have a look at what we're finding the inverse tan of, it's this square root of 3 minus x squared. So there will be a restriction because we know whatever is under that square root sign has to be greater than or equal to 0. So the domain for our function will be minus 3 to 3. Now, because we've restricted the domain, normally the inverse tan function will go all real x. But we're now restricting it to be between minus root 3 and root 3. Well, that's going to have an effect on the range. So let's sub in the endpoints. So I sub in root 3, I get inverse tan of 0, which is, of course, 0. Minus root 3, well, it's x squared, so we get the same answer, 0. Sub in the middle of the range. Oh, sorry, middle of the domain. Sub in, we get pi on 3. So it looks like our range goes between 0 and pi on 3. So endpoints and the centre usually covers it. Because we usually find these trig graphs are symmetrical and things like that. But if you're unsure and you want to test a few more points, you just pick some more points to see what's happening. So what does it look like? Okay. So there's pi on 3. Minus root 3. We knew it was 0 at the root 3 and the minus root 3, and we know it goes up to pi on 3, some sort of shape like that. So y is inverse tan of root 3 minus x squared. Now, once we've done a bit of calculus, we could work out whether indeed that is a stationary point and things like that. Inverse sine of sine x. Well, the temptation to say is, well, that's just the line y equals x. Not quite. It is based on the line y equals x. Let's have a look at the domain. Because remember, it's an inverse sine function. So I can only substitute in things in between minus 1 and 1. So I'm now saying sine x has to be in between minus 1 and 1. When is sine x in between minus 1 and 1? When? Always. So the domain for this is all real x. I can substitute anything in and get an answer out. So maybe it is the line y equals x. But what about the answers? It's still an inverse sine function. So it can only spit answers out between minus pi and 2 and pi and 2. So hang on, it's all real x. It's y equals x, but can only go between minus pi and 2 and pi and 2. What's happening with this graph? So let's draw some points in. We'll go up to, well, there's pi minus pi and 2. So we've said, all right, we know that bit for sure. There's y equals x, but I've stopped at the minus pi and 2 and the pi and 2. What's going to happen for the rest? Well, I could test some more points. I could sub in, say, pi. Sine of pi is inverse sine of 0. So it must be back to the x-axis there. I could sub in minus pi. Similar thing's going to happen. As I sub more points in, I find, it's a zigzag. All the way along the x-axis, we've got this zigzag going up and down between pi and 2 and minus pi and 2. So it is based on y equals x, but it's not exactly that. It's just that straight line going up and down, up and down. What about the other way around then? The sine of the inverse sine of x. Now normally the domain for a sine function is all real x. But we're substituting into the inverse sine of x. Therefore, we're now restricted into what we can substitute in. I can only substitute numbers in between -1 and 1. Okay? But if I substitute in numbers between -1 and 1 for the inverse sine function, well, let's see. We've restricted the domain. At 1, I get the sine of the inverse sine of 1. Turns out to be 1. At -1, I get the sine of the inverse sine of -1. Turns out to be -1. At 0, I get the sine of the inverse sine of 0. Turns out to be 0. So the range looks like it's going to be just -1 to 1. Again, it is y equals x, but this time it stops. It stops at -1 and 1. So to draw it, and this time there we got 1 minus 1 up to 1 minus 1, it is simply just that piece of y equals x. So there actually is a difference between the two curves. The inverse sine of sine x, we got the zigzag going all the way, whereas the sine of inverse sine is just a piece of the line y equals x. Okay, handful of questions out of 1C, some different graphs to have a go at there.